So, in the last class we looked at the basics of heat transfer in single phase flow, some basic definitions, and then some typical characteristics of heat transfer in the Taylor flow regime. Based on those, based on the understanding that we developed in the last class, let us try to develop a general correlation for the heat transfer in the Taylor flow regime. Of course, we would need to make some assumptions to make this a closed system of equations, so that correlation which can be used, or a system of equations which can be used to predict the overall heat transfer in a unit cell for fully developed Nusselt number in a channel. So, before we go on, let me try to say a few words or sensitized you a bit about the fully developed Taylor flow, because our general definition of fully developed is that for velocity we say that del or dv z over dz is equal to 0, and d theta over dz is equal to 0. My apologies, because I keep exchanging this bit either x or in z. Probably you understand that these are, whenever I use these, most of the time it is referring to axial coordinates. Sometimes I call it x and sometimes I call it z. So, this is true for single phase fully developed flow. But when we talk about Taylor flow, it is not possible to achieve this, because the velocity at the middle of the bubble and the velocity in the liquid slug, or even in the liquid slug at two different locations, is going to be different. So, what we mean by fully developed Taylor flow, or what somebody else mean by fully developed Taylor flow, is that the flow has become fully periodic. So, if you look at two periodic locations, then the flow has achieved periodicity. So, if you compare the velocity at two periodic locations, then they should be equal, then it has become, flow has become fully periodic hydrodynamically. So, the model that we present here is based on Professor Brian Haynes and his students and collaborators, Professor David Fletcher. So, what we are looking at in this plot is, along the distance, the temperature, and there are two different temperatures have been plotted: the temperature at the wall of the channel and the temperature of the fluid, or the bulk temperature of the fluid. And this has been done for a number of bubbles, and it is a snapshot in time. So, one can look at the different bubbles from the inlet, and the wall temperature is changing. So, it has not become steady yet, it is almost. So, what we look at, that the temperature is increasing continuously, and these are the this is the non-dimensional radial location. So, this is from 0 to 1. So, that is basically small r by capital R, and this is the wall of the channel, and the blue symbols represent the shape of the bubble. So, one can look at the temperature of the liquid and the temperature of the gas, both of them decreases, but there is a jump here. So, if we look at the corresponding location, for example, this point and this point, there is a corresponding increase in delta T, and similarly there is corresponding increase in delta T here, and at the same like this. So, there is a increase in temperature in both the places. So, when the flow becomes fully developed, then delta T in a unit cell is a constant, and it will also require that the temperature of the two phases. So, the temperature of the continuous phase and the temperature of the dispersed phase, the rise in the temperature of the continuous phase and the temperature of this dispersed phase are same. Okay. So, based on this, we can write the heat flux Q by the dispersed phase is equal to m dot dispersed phase CPD into delta T of dispersed phase. Similarly, the Q for slug will be equal to m dot slug Cp slug, or we can say, because what we are looking at rather than slug, we are looking at here is the continuous phase, which is slug plus the film. So, m dot C is Cpc delta T continuous phase. Now, based on this, we can get, because delta T of dispersed phase and delta T of continuous phase is going to be same. So, we can basically obtain Q d over Q c is equal to m dot d CPD over m dot C CPC is equal to m, and the total heat that will be coming from the wall. So, Q wall in a unit cell will be equal to Q d plus Q c. So, one will have Q d over Q wall is equal to m over 1 plus m, and Q continuous phase divided by Q wall is equal to 1 over 1 plus m. We can also write m in terms of rho d into beta Cp d divided by 1 minus beta rho C Cpc. We will have in both the cases u here, but then the u will cancel out. So, that is the definition of m, basically the ratio of the thermal mass flow rate multiplied by the heat capacity. Okay. So, that is an important relationship, that how much or what fraction of the heat is going to the dispersed phase and what fraction of the heat is going to the continuous phase. If d is gas, so then we can see that m, because beta and 1 minus beta, they will be equivalent numbers, Cpc are also of equivalent, and so because rho gas is very small when you compare with that of liquid. So, m is almost negligible. So, you can neglect and most of the heat. Then this shows that for gas liquid flow, the heat goes in the liquid phase only. Okay. Now, we will define the bulk temperature. So, bulk mean temperature can be defined as integral for a unit cell rho u Cp T dV divided by integral for a unit cell rho u Cp dV. So, in an average we can write this, because rho u is rho u dV refers to the mass flow rate. So, we can write this as m dot for the dispersed phase. Actually, we can consider 3 phases or consider 3 zones. Consider droplet or bubble, film and slug. M dot D CPD and temperature of the dispersed phase plus m dot film Cp of the continuous phase, because film is in the continuous phase only, and this is temperature of the film, plus m dot slug Cp continuous phase temperature of the slug divided by m dot D Cpd plus m dot F Cpc plus m dot S Cpc. So, we can neglect the flow rate in the film. So, we are neglecting the mass flow rate in the film. That means, we say that m dot film is small compared to m dot D or m dot slug. So, if we do that, then we have this relationship turning as m dot D Cpd divided by m dot S Cpc Td plus Ts divided by m dot D Cpd over m dot S Cp C plus 1. Now, this is approximately equal to m. Why approximately? Because we have neglected the mass of the film in both the cases for the continuous phase. So, this Tb is m Td plus Ts over m plus 1. So, one of the approximations that we have made in this case is that we have neglected the mass flow rate in the film, okay, which is quite okay if we are using for gas liquid flow, but for liquid flow or for film that surrounds the slug, that is not that may not be the case. Okay. So, now we will be looking at the heat transfer in the droplet regime. So, the picture that we have in this case is like this. We have a continuous film in which there is a stream of continuous phase which is slug, and disperse phase, which is drop or bubble move. Now, we can treat the films in the slug and drop. So, it is very clear that there is a film surrounding the droplet or surrounding the bubble, because this is of continuous phase. However, for the slug, one need to think a bit, because the liquid recirculates only in the middle region, and then beyond this recirculating region there is a small film, and this film, the thickness of this film may or may not be same of the film surrounding the droplet or bubble, but for our analysis we will assume the two films to be equal to simplify things. So, what we are going to look at in this case is account for the resistances in the droplet region. So, we will draw it again, the channel wall, a droplet, and the heat entering from the wall, the heat flux being Q W, and then it comes into the film, and from film it enters in the droplet region, and so on. So, the temperature difference T wall in the droplet region. So, the temperature of the wall is TWD minus T droplet, which is temperature of the droplet. We can also write this as, this is the film. So, the film temperature we write as TFD, or the temperature at the interface between the film and droplet. So, we can write this as TWD minus TFD plus TFD minus TD. So, we have just subtracted and added the film temperature. Now, we can write this T wall minus TFD is equal to Q wall, that is the heat coming in, divided by the heat transfer coefficient. So, delta T is equal to Q wall over H, and that will be H of wall in the droplet regime. We will neglect any difference. So, we are going to assume HWD is equal to HW slug regime. So, and that is when we do this, when we write this equation, we also neglect So, when we neglect the convective effects, basically we are writing so we will do that later on anyway, but by doing this approximation, what we are saying that delta F in the slug region will be equal to the delta F in the droplet region. So, that is Q W over H W in the droplet region plus T F D minus T D. So, T F D minus T D will be Q F D divided by H F D. Now, Q F D over HFD. So we can write this expression as TD is equal to TWD minus QW into 1 over HW plus QFD over QW 1 over HFD. What we have done is we have taken TD on this side and wrote like this: TW minus QW has been brought out. So, 1 over HW, we have just approximated this HW, dropped D subscript here, plus QFD over QW, because QW has come out. So, we have a QW in the denominator into 1 over HFD. Now, we need to write this QFD. So, because we knew that QD over QW is equal to M over M plus 1, you can remind yourself from here. QD over QW is equal to M over M plus 1. So, that gives us QFD over QW is equal to QFD divided by the droplet region. So, that will be 2 pi r length of the droplet. Remember, this r is, we are approximating r is equal to r droplet. So, we are neglecting the film thickness in this case, divided by QW over 2 pi, this is QW for the entire unit cell. So, that is why we have 2 pi r L UC. So, 2 pi r will be cancelled out, and what we have is QFD over QW into LUC over LD, and we can substitute QFD over QW as approximating that QFD is about same as QD. So, we will just talk about in this in a minute. M over M plus 1 LUC over LD. Now, why QFD over QD? So, the heat, what is QD? QD is the heat that is being entered in the droplet. Now, the droplet can have heat entering from the film region and the two caps. So, by doing that, we have neglected heat transfer from bubble, or because we are using droplets. So, from the droplet caps at the front and rear. Okay. So, when we substitute this, then we will have temperature of droplet is equal to T wall D minus QW (1 over HW plus M over M plus 1 LUC over LD 1 over F droplet. Similarly, for slug, one can write T slug is equal to T wall slug minus QW 1 over HW plus 1 over M plus 1. So, we have this as because now it is slug. So, the heat will be 1 over M plus 1 and LUC over LS 1 over H F slug. Okay. So, we have a relationship between the temperature differences and all this. Now, next let us substitute this slug and droplet temperature in the bulk temperatures. So, we had this bulk temperature TB is equal to M TD plus TS divided by M plus 1. So, we can substitute the two values from here and we will get M over M plus 1. So, we can write this as 1 over M plus 1 and we will have M plus 1 TW. Ideally, we will have we add these two terms M TWD plus TWS. So, another approximation we are going to make here that or what they have made in their correlation is TWD is equal to T wall slug is equal to T wall. So, that means saying that the temperature at the wall is same in the slug wall temperature is same in slug and bubble regions, bubble or this approximation is more valid in the droplet region where the heat capacity of the two phases will be of the same order. So, the temperature will be about same for the two phases. Okay. So, this is M plus 1 TW minus QW into M over HW or M plus 1 over HW plus M square over M plus 1 LUC over LD 1 over H FD plus 1 over M plus 1 LUC over LS 1 over HFS bracket closed. So, now we can substitute, we can expand this and we see that TB is equal to T wall minus QW over M plus 1 and this entire thing in bracket. So, we can just represent this entire expression in the by the middle bracket to each things out. So, the entire expression is we copy here. Now, when we substitute this, then we will get TW minus TB is equal to QW over M plus 1 and we can define an H overall HUC is equal to Q wall divided by T wall minus. So, this will be the T wall minus in Q wall into this bracket, and entire thing in the bracket. So, HUC is equal to Q wall divided by T wall minus T bulk. So, from this relationship we get 1 over HUC is equal to 1 over HW, as one can see this m plus 1 and m plus 1 will cancel, plus m over m plus 1 squared, m square, and we have one more m plus 1, LUC over LD, 1 over HFD plus 1 over m plus 1 squared LUC over LS, 1 over HFS. So, this is a relationship between the overall heat transfer coefficient wall, the heat transfer coefficient at the wall, and m, which is the ratio of the thermal mass of the two phases, slug length, entire unit cell length, and the heat transfer coefficient for the FD and HFS. So, if you look at now, what we need is that overall heat transfer coefficient is a function of 3 heat transfer coefficient, H wall or the film heat transfer coefficient, H film to droplet, H film to slug, and m, which is ratio of the thermal mass, and LUC over LD and LUC over LS. And what else? Yeah, so these are the factors. So, these things we can know from the characteristics of the flow. Now, what we need to know is are these 3 coefficient HW, HFS and HFD, and if we know, then it becomes a closed system and we can calculate the overall heat transfer coefficient for the Taylor flow regime. So, as we have already discussed that we have assumed in this case that the wall heat transfer coefficient for the slug and droplet regime is assumed to be same, and we can consider only conduction. So, HW is equal to K over delta film, where K is the thermal conductivity of the convective phase. So, we neglect any convective effect in the film. So, the pure conduction will give heat transfer coefficient is thermal conductivity divided by the diffusion length. So, this is delta F, and delta F one can obtain from Berthoudin's correlation or oscillation square correlation, which is 1.34 Ca, which is capillary number raised to the power 2 by 3 into 1 plus 3.35 Ca raised to the power 2 by 3, where Ca is capillary number defined as mu u over sigma. Okay. Now, for slug heat transfer coefficient or HFS, because if we look at the flow, in the slug which is moving, it has an analogy with the developing flow. So, a similar correlation that is used for the developing flow in the liquid only flow case, or this liquid flow in the channel, it is used, which is for the H boundary condition 4.364, which is Nu for fully developed liquid only, plus A1 by Ls star plus A2 Ls star raised to the power 1 by 3. So, where Ls star is inverse Grudget number, or Ls over D Reynolds number Prandtl number. Okay. So, by fitting their data for the experiments, it has been found that the values of A1 and A2 are 0.171 and 0.0663, and so that correlation gives the heat transfer in the liquid slug. Using similar arguments, they have also obtained a relationship for this is not fully developed. So, this is film to droplet. So, the Nusselt number is 4.364, the same correlation, but A1 and A2, these are same as for liquid only flow. Okay. So, one can obtain the Nusselt number for the liquid only flow from this correlation, and then if this becomes system of equation becomes closed. So, one can calculate the overall Nusselt number for in a unit cell in the Taylor flow regime. So, basically in this lecture what we have done is we have looked at a simple model based on the fundamental principles for the overall Nusselt number in a Taylor flow regime, or in a unit cell which consists of a droplet or a bubble and the liquid slug. The model is based on the assumption that there is a continuous thin film of liquid on the wall, and the droplets and slugs, the stream of droplets and slug move over it. There are number of assumptions that we have made along the because to make the system of equations to be closed. One of them is that the film thicknesses in the around the slug and around the droplet, they are same. This may not be the case every time. Another assumption that has been made, that the heat transfer to the droplet phase is happening from the film, or from to the slug phase is happening from the film only, and there is no interphase exchange at the interface between the two phases. Okay. So, once to calculate this, we need to calculate the heat transfer at the wall, which can be done by assuming only pure conduction in the channel wall, and the correlations for heat transfer coefficients in the droplet and in the slug flow regime, they are calculated based on the developing flow correlations for liquid only developing correlations for developing flow for liquid only flow in a channel. Okay. Thank you.